All right. All right. So in the training example, what you do is basically you have an input and you break it down into training set. All right. And then you see whether the other input belongs to any of them. Okay. So because whenever you are doing predictions, okay, whenever you are doing predictions, how will you test a predictor? By testing against the historical data. That is why you typically take out 20% of the data set and keep it aside for testing. You feed the training data into machine learning algorithm and observe the testing, compare it against testing data and observe the result. All right. So let's take this case where what we are doing is we have a binary.csv. It has got house locality and fraud. Okay. Now we want to figure out a relationship between house locality and the fraud. All right. So here what we have done is we have done a sampling of number of records, and we have picked up some records from that. And once we do that, we basically pick up all the data from my data and put it in the train. And here, rest of the, so this is my indexes. These are some random indexes. That random indexes, based on those random indexes, we are picking up the data and for training and for testing. So we prepared two data sets, and once that is done, we will do the after stratifies random sampling, the proportion of the training data and in the real data will always remain constant when we do the stratified random sampling. In data set, 30-70 ratio is the ratio of fraudulent to normal data, so that the same ratio will be preserved for training as well as testing cases. Okay. So we picked up again the same thing, index 1, index 2. Okay. Now here a few things you should note is out of my data, if the value is 0, that means there is no fraud. If that particular column is 1, then there is a fraud. So we prepared a binary data out of it. Okay. Based on this, okay. So that's what we did. Good. All right. So out of this data, what we have just prepared, we picked up randomly something, some records, and finally we have training data set ready. It contains two vectors, 1 and 2. Basically, two set of rows where there are one set of rows which says the fraud, and the other set is no fraud. Okay, that's my training data. All right, and this is my test data, where I have bound the rows from the fraud. So we have prepared these two data sets, and then we do the evaluation. So all in this example, what we have done is we have taken the records and then sampled it. 70% go to my training set, 30% go to the test set. In both the cases, fraud and non-fraud, means positive and negative both. Okay. Similar to classification problems, statistical inference problem, classification is also prone to misclassification errors, meaning we marked something as something was an email, the ham, we marked it as spam, or there was something as a spam which we marked as ham. Okay, so false positive refer to the observations classified as positive, but they are actually negative, while false negative are just opposite. Okay, a seemingly simple scheme named as confusion matrix or coincidence matrix is used to calculate the performance related to the entries. Okay, many parameters are calculated using confusion metrics such as accuracy, specificity, sensitivity, precision, recall, and finally receiving operator characteristic curve, in which area under the curve measure provides the peak into overall usability of the classifier. Okay. Now the confusion matrix is this: what is predicted against what is actually there. So if predicted is spam, we are trying to predict spam. If it is actually spam, then we are truly positive. If we predicted as spam and if we predicted as non-spam and it was not spam, then it is truly negative. If we predicted something as spam, but it was not really spam, that is false positive. Then we predicted as something as not spam, but it was actually spam, that is false negative. Okay, the accuracy of such a model is what? Can you tell me? Say 5 were truly positive, 5 were truly negative, 10 were false positive, 1 was false negative. 5, 5, 10, 1. What is the accuracy of such a system? Accuracy is how much did they do correctly? 5 plus 5. This is the accuracy. 10 divided by 10 plus 1, which is 21. So 10 divided by 21 is the accuracy. 5 plus 5, 10 plus 1. So 5, 5, 10, 1. So total is? No, 10 by 21. So 5 plus 5, 10 plus 10 plus 1. Okay, yeah. Okay. So this is overall accuracy. And the error is 10 plus 1 divided by 21. Okay. So accuracy plus error will always be 1. All right. Now you're clear to you? Can you go back to the previous again, please? Correct? Clear to you? Now sensitivity is all right, truly positive divided by truly positive plus false negative. Okay, that is our sensitivity. Sensitive means really we predicted correctly divided by predicted correctly and also mispredicted incorrectly. Okay, truly positive and false negative. So you can see that. No, truly positive divided by false negative. Truly positive divided by false negative. Okay, yeah. All right. What does it mean by sensitivity is truly positive divided by truly positive plus false negative? Okay, what does it mean? Let's say our model is super active. Okay, if it starts saying 1 1 1 1 for everything, okay, it starts saying that everything is positive. Okay, false positive. This is false positive. So when our model is saying something is incorrect, all right, the ratio of saying something is negative and it's not negative and total number of positive. So this is called sensitivity. So specificity is truly negative divided by false positive. Okay, that is specificity. So the points comprising ROC curves indicate the true positive rate at the various false positive threshold. Perfect classifier has a curve that passes through the point at 100% true positive rate and 0% false positive rate. All right.
What does ROC mean?
This is called ROC curve. We were talking about this. Receiver operator characteristics. Okay. Receiver operator characteristic curve is something which basically is used to test how great is your classifier doing. Okay. A perfect classifier has got a curve that passes through a point at 100% true positive. So this is false positive and this is true positive. So 100% false positive is 100% true positive is this line. So a perfect classifier basically passes through this point. Okay, passes through this point. All right. So basically, all it means to say is the perfect classifier is the one which gives 0 false positive and 100% false negative, true positive, meaning this point. All right. So if there is a classifier which does not do any prediction value, okay, which will have equal false positive and truly positive rate, equal both. Why? If it just does a coin toss, okay, it just a coin toss, and if a record is coming in, sometimes it's saying true and sometimes it's saying false. So still it'll have 50-50 both, right? So if my classifier is like this, will be perfect classifier, and area under this curve measures the health of the classifier. Okay. All right. So if the area under the curve is 1, as in outstanding, 1 is outstanding and less than 0.9 is excellent, 0.8 is acceptable, and 0.7 is poor, and 0.6 is no discrimination. Okay. So that was a general classification problem theory. If you have to do a logistic regression, you can consider the data where target variable is binary, meaning the outcome is yes or no. Is this a spam or no? That is a recipe for logistic regression. We use logistic regression in the cases of the outcome is true, yes or no. Rather than modeling this response as yes directly, logistic regression models the probability that yes belongs to a particular category. Okay. So All right. Basically, imagining that y and n are two factors in the data, we will model the whole thing. All right. So since the range of probability is 0 and 1, we need to use a function that can give an output between 0 and 1 for all the values of x. Okay. Given a values of x, we have to predict 0 or 1. But in our model, we'll try to make it decimal. The more, the better. Okay. So loan default prediction using deposit bank. Okay. It has got a balance and it has got a probability of default. Okay. If the balance keeps growing, there is a probability of default. Okay. Consider a case where you want to predict the probability of default on loan given the saving account balance of the customer. You want to model to provide a default probability score between 0 and 1 given the account balance. Okay, so we are given the account balance of the users, and we want to prepare a model where we can predict the behavior, we can predict whether a user will default or not on their loans based on the account balance. Okay, the above function will always produce S-shaped curve given above, and so regardless of the values of x, so you'll get a sensible values of probability. All right. E to the power beta 1. These are two constants, beta 0 and beta 1. Okay, it's a function of x. So this always gives us the value between 0 and 1. Now, if you compare it with the linear, the right hand side is not a linear function of x. Okay. So we cannot use a linear regression in these kind of scenarios. If we convert the right hand side to a linear function for simplicity of understanding, we would be able to model odds of any event happening instead of probability directly. Okay. So if we try to, okay, we can convert this expression into this, and we will have something like b0 plus b1, and this is linear. All right, this is linear. The output of logistic regression is similar to linear regression. The variables having specific p-values less than 0.05 are used in the expression. In the above result, the odds of default could easily be found out using a simple expression like this one. Okay, and then once you have find out this side value, we can do the inverse computation and find out the actual values. All right. We are continuing the study which we were doing earlier. We were doing a fraud detection, right? We prepared two set of records, one with fraud, other with non-fraud. Okay. So here we are trying to build a model. Okay. Here we are using a function called GLM, which is for logistic regression. Okay. So what we are doing is my logistic regression equals to GLM, fraud against debt plus loan by annual income plus house locality and so on. Okay. So we are trying to do a logistic regression between these 3-4 variables. Data is this my data, and family equals to binomial. All right. Once we do that, we are saying summary my logit. All right. And afterwards, we are saying within this data, find a relevance level of these two. Okay. After that, okay. This is nothing but feeding these variable into creating an object called a training model, and afterwards we are plotting. We are basically doing the logistic regression, fraud against that plus loan by annual income plus house locality, and our based on this data, and we are saying that it's a binomial regression. Okay, and this way all right. All right. So here in the earlier one, we were using the full data. Here we are using skipping few records and then forming the graph. Okay. And afterwards, after we have done the prediction, after we see in the previous one we prepared something called my logic, and this one we can use the predictions, and the predictions whatever we receive we can prepare ROC over predictions and then plot the data. All right, and this way uh, we can do the we can compute the performance of our predictions using a performance and then plot the performance chart. All right, so yeah. Okay, so these are few packages which can help you doing the logistic mm, data modeling. I'll show you. So what all data we wanted there? Okay, my data underscore train is what we want. Where is my data underscore train? Yeah. So we say my data and we are reading the CSV. Okay. So my data is there. My data contains these records. So I can also say things like view of my data, and here you will be able to see the view. So we have got fraud, yes or no. Okay. That was this much. Loan by annual income was this much. House locality was located at this place. So did he do the fraud? Yes or no? Is there a relation between these three input variable against this? All right. Next is, let's say my data house locality, I'm converting that to factors. Okay. So now this is a factor now, the last one, so that it takes less value and easy to do the manipulation. Okay. Similarly, the fraud to yes or no, true, false, I've converted into factors. All right. Now, out of this, we are saying randomly pick up the indexes. This basically are the indexes out of 320 records. These are 320 records, right?
Yes.
No, these are 400 records.
But here, showing only 320 since
Where?
down.
Yeah. No, this one we have only picked up 320.
Okay.
Why? Because out of 400, we want to pick up only 80%. Okay. 40% we are leaving. So out of 320 indexes, we randomly pick up the numbers, and some we make test and some we make train. Now we can say my data underscore train has these many records, and my data underscore test has got 4 records only. No, it will have more records. I'll show you. The 80 records. All right, it has got 80 records. Now that is our all right. Now let's use this data in the example which we were talking about. Okay. So this is our logistic regression where we are saying that okay. So my logit is this. All right. So we have done fraud against debt, loan by income, and house locality. Instead of saying LM, we are saying GLM. Okay, and we are saying binomial. Right? We can see the summary. See the summary. It shows us the details about the full data. It shows that what is the minimum of the residuals. Residuals means the difference between the actual to the real value. Okay. So it shows that this is the median, this is the max, this is the min, and so on. All right. Now, here we are saying we are just let's just within this data we are releveling, meaning changing it to changing the factors. I think relevel is for changing the factor. Yeah, reorder levels of factors. Okay. My data underscore train, and now again all right, so we are able to do some computation on top of it. All right. So next is once that is done, we can do the prediction. Let me just install these packages. What's why it's not done? Oh, I got it. There is stupid double quote. All right, it will download and install. Till then, let me fix this. I had changed it earlier. It's downloading this package called ROCR. Okay. All right. So ROC curve, the one we were talking about, it is used in those cases. So have you installed everything? All right, let's try to execute this. So area under curve is 0.5327, which is okay. All right. not okay actually. It should have been, because it's like a linear in the center. Should have been at least this much. Okay, meaning how much ever it's predicting, it's also predicting that many true false positive. Okay, that means it's 50-50. All right. So this way you can do your performance analysis of the thing. Yeah. It's not a great model, but it still it's giving some results. It's doing 50-50 analysis. Maybe if there is more data, then it will make more sense. All right. Now, lot of these techniques, the statistical analysis, linear regression, multilinear regression, and logistic regressions, they suffer from the problem that they cannot solve all kinds of problems. And they all need a lot of human intervention to be solved. Sometimes we realize that there is no linear relationship between input variable and output. There is no logistic relationship between input and output. And so we do a lot of back and forth to actually analyze. Sometimes we feel that, oh, it's a Fourier series and whatnot. So this graphing techniques that we have used, linear was good. Simple linear was good only in the cases when there was single variable. Multiple linear was good only in the cases where multiple variables were there, but they had a direct relationship. If there is a multiplier effect somewhere, or there is a square root, a square, or e to the power something, then that linear regression completely fails. Multiple linear regression completely fail. Similarly, even in the cases of clustering, it becomes impossible to cluster the data where the data is in this manner. Look at this data. If we said, give me two groups, it's very obvious that there is an outer circle and there is inner circle. Okay? Our techniques of clustering the data will never give this result. Either it will give like this and like this, or it will divide it into two parts, but it will never give this. But a human can give this result very quickly. Look at the data and see, oh, there's an outer circle, there's an inner circle, and this is the two clusters. And therefore, none of the techniques what we have studied in linear regression, multilinear, or our traditional clustering does not solve the visual problems. Okay, what is visual image identification? Image identification is figuring out the clusters of the values on the image and clustering the correct things together and making an object out of it. When we look at this wall, we say that there is one square, there is another square, there is another square, and there seems to be a wall and there seems to be a roof. So visually, we are able to figure that out. Okay, based on the past experience, we are able to cluster things, and that's a visual identification. So most of the techniques fail pathetically when it comes to complex clustering or complex predictions. And this is where the neural networks really work. Consider a data where there is a chance that the target variable is non-linearly related to independent variables. In such cases, LR is relatively incompatible and incapable of capturing the true relationships. Rather than modeling this non-linear response, if it can be converted to linear by changing dimensionality, modeling can be very easy. All right. So same way, we have got this kind of data. If we change this to polar coordinates, it will become really simple. Okay, it will become really simple. What is polar coordinates? Polar coordinates is one point here and this distance r and theta, r and theta, r and theta. So as r remains almost the same, here the center point r remains the same, and the theta is only increasing. So r remains the same, theta is increasing. Okay, so you can see that this is r remains from the center, theta is increasing. R remains, this is for the outer one, the r is little bigger, radius is little bigger, and theta will remain same. So if we just plot the same graph, from to angular one, then we'll be able to solve the problem. But it's not an easy task. And that is where artificial neural networks do wonders. And what is artificial neural network? Let's first understand what is the neuron. How does the brain work? Brain has got something called neuron. And a neuron is, it gets a signal from the inputs. These are input signals. And it has something called a summation, a function, which has got some weightages to each value, weightage 1, weightage 2, weightage 3, and it multiplies the signal value x1, x2, x3, and then sums them up and gives the output. Okay, so now you can see that there are 6 variables here. There's an input response coming in. Each input neuron has given a weightage to each. In the neuron, this gets multiplied, these two gets multiplied, and then the resulting value is summed up, and then output is given. So to this neuron, there are 3 inputs going and 1 output coming out. All right. So now imagine these neurons connecting to another neurons over a layer. Thousands of neurons connecting to each other. And now there will be thousands of input variables, 1 output variable coming out. You put the data, it gives out the output. And on what basis it is going to give the data? So initially we train each neuron or the layer of the neurons with the input and output. And based on that, each neuron computes its weightages. And so basically it computes each weightages, and so do all the neurons. And this computation of weightages is called the machine learning. It's called the neural network learning. What? Other neuron? Yeah. Now imagine the same formula being applied by all the neurons parallelly, so that the input is coming and being applied. All right. So we have got input variables, we have got output variables, and this is the black box. And this black box contains layers of neurons connected together, and computing all its weightages all the time. And this is how the brain works. This is how we learn anything. These neurons figure out the weightages of various things, and then based on that, they given the input, they say this is the output. Given the input, this is the output. All right. The aim here is as well to minimize the training error, but is a resource consuming task, and so training is a costly activity. So training a neural net is very, very costly, while using a neural net is very easy. If you download the weightages from somewhere, if somebody has already prepared weightages for the whole neural network, so what will happen is they will give you all these weightages. They'll also tell you how many neurons are in which layer. Now on your local machine, you can quickly assemble it, and then given an input, it will immediately give the output. Okay, which means a trained neural net can be used on low-end devices as well to predict. But learning is a costly exercise because it has to compute W1, W2. There are thousands of such variables which it needs to compute. Okay. So it can do any kind of predictions. Can use multiple activation function depending on the need and other constraint, domain specific applications. All right. So this is the error. The output and the root mean square value divide by 2. All right. You can try to use this. So all we have to do is download neural net package and read this data called concrete.csv. So you can see that I'm installing libraries. It's directly downloading. Okay. So I've downloaded a package called neural net, and I am reading a concrete. So let's see what is there in the concrete. So here, what?
You can be helpful again.
I think view will be better, right?
Yeah.
All right. It has cement, it has slag, ash, water, superplastic, and coarse aggregator. So these are of my input variables. And based on this, I want to do some predictions. All right. Based on this, I want to do some predictions. All right. So also a string concrete will make sense. You can see that. So let's first normalize it. Normalize means converting it into a value between 0 to n. Okay. So function x says minimum x minus minimum of x divided by maximum of x and so on. Okay. So we can apply normalize into the whole concrete. This is what we are saying as a data frame, convert it into a data frame and keep concrete underscore norm. So again, let me represent it as a view. So you can see that all the values have been converted into 0 to 1. That makes our life easier. All right. All the values have been normalized. So these kind of tasks, you see, normalization is just immediate for this. All right. So let's divide the data into 2 sets. Okay. Training and test. And model becomes here. This is the model. You see, it's pretty straightforward. We are saying neural net strength against. So our what we are trying to compute is the strength actually. Okay. Here, do you see strength somewhere? The last column. So we are trying. Strength is our output variable based on cement, slag, ash, water, superplastic, coarse aggregator, fine aggregation, and age. We will predict the strength. Given these input variables, how is our strength related to these variables? Okay, so that's what we are trying to predict. Let's say we pick up this. Okay. Where is my graph? Now you see that? So here, what the most important part to understand is each neuron behaves like a linear multilinear regression. This variable is dependent on these things, where there is a weightage which we have found out just now. This equals to this multiplied this, this multiplied this, this multiplied this, this multiplied this, and so on. That's what we have done just now. So if you have a single neural net, then it will look like that way. All right. Now model results are these. Okay. So if you see model underscore results so what we are doing is, now we had kept some records aside for testing. We are trying to compute the model result, basically compute the results from this model, from the predicted set. Okay. These are the results. And now predicted strength is how much? Predicted strength for them will be an array for these many. Now let's compare predicted strength versus our actual strength. Okay, so there is a strong correlation between my predicted strength and concrete strength. Now let me show you that. So let me just view and say C. Okay. Why it's not showing that? We can say C bind, right? Yeah, now you can see that. On the left hand side is our predicted strength, and on the right hand side is our actual strength. You can see there is a strong correlation between the two. Correct? So we are just comparing how great is our value here. All right. If we plot it, the relation is almost like a straight line. Actually, a better thing to do would be, yeah. So you can see that we were able to do the prediction using neural net in R. Make sense to you? So the only thing we need to know is the few things we did. First, we loaded the data, then we normalized it. How do we normalize? X minus minimum of X divided by maximum of X minus minimum of X. Okay. So that's how we normalize. Find the maximum. If there is an array, find the maximum, find the minimum, divide the delta by the maximum difference, and that's it. All right. So first we take an array, we offset it to the minimum we set it to 0, and accordingly we set everything else. Now we divide this array, each element of this array, by the maximum element of this, and that's how we get the result. So we took an array, offset it to 0. So if we have, this is important to us actually. So if we have 1, 5, we have this, and 9. So what will be our, let's say, so now it's actually so easy, right, for you to actually do things quickly using R. So we have got this array. Let's normalize it. What will I do? So minimum of A, maximum of A. Now, so A minus minimum of A. And let's assign it to A. Now,
Maximum minus minimum.
A. So minimum is 0 anyway.
Okay. So we will not do difference between minimum and maximum.
Right. That's 0 anyway, right? Minimum.
Yes, yes.
A divided by maximum of. See, so we have converted the array such that minimum becomes 0, maximum becomes 1, and all other elements are in between. Right? So that's called normalization. It's a very important technique in almost every predictions. All right. So we were able to plot the graph. All right. All right. So there is something called SVM. It's called support vector machines. SVM is a very powerful idea. The idea here is more from geometry. Okay. An effort shall be made to draw a hyperplane that divides the point into two separate groups. Okay. You have got these points, and we want to draw a plane such that it divides the points into groups. But the problem is that there could be multiple such planes. There could be this plane, there could be this plane, there could be this plane, there could be another plane. All right. So we want to divide this. So how should we define the best criteria? All right. So instead of defining a single separating line, we define a margin instead of a simple plane with a maximum width before it touches any of the points. Okay. So we figure out a point just before it touches any plane, and the reference point which define the width of the margin are known as support vectors. Okay, the reference points which define the width, this width, are called support vectors, which is this, this, this. All right, these are called support vectors. But what about linearly inseparable data? Let's say our data is like this. Okay, we can, if you have to make the group in this manner. Okay, what happens? Okay, so similar to that, the solution here is using nonlinear kernels, making the margin nonlinear. Popular kernels are Gaussian, polynomial, neural net, etc. Okay. Now here is the identifier. So what we are going to do is we are going to, given the images of letters, we want to predict which letter is it. You know OCR? The OCR is given a character glyph, it predicts which letter is it. Is it A, is it B, or is it C, or is it D? Okay. So first it will normalize the data to fit into a frame, and then it will do the other math. Okay. So we will show you that. Now let me pick up something called a kernel lab library. It is downloading. Then what we are going to do is we are going to read letter.csv. We have got letter.csv. I'll show you what does it have. So let me go into my R course. Here there will be examples, and there is something called letters.csv. Yeah, this is the letter.csv. Okay. The image of each letter, say letter T, has got X box, meaning the length of the X side, Y box, which is the length of Y, and the width is 3, height is 5, and so there are various kinds of criteria which have been developed from the image. The X side image it starts at 0, X as Y and at 8, and so on. All right. So these are the characteristics of the photo of these images, all of these images. Now, given image, it should be able to identify which letter we are talking about. The identification of an image from into a character. All right. So this letter.csv contains these details about all the letters. And the important part is that there are multiple times one letter is there. So you can see that T is there again, yes, and T is there again. So these are the various characteristics of T. All right. From this, we have to automatically figure out the letters. Okay. So now let's read this file letters.csv and check what has come. So now we have loaded letters. You can see the letters. All right. Now string letters, you can see that. And then we say we separate training data and test data. Okay. So first few records go into training data. Next records go into the. So 4,000 records go into the test, and 16,000 records go into, again, 80-20 ratio. So we make two sets. Let's say letters underscore train. You can see that. And once we have done that, so here, okay. So we say KVM, okay. We say KVM, letter classifier equal to KVM, okay. And we say dot. Dot means all. So first column is letter, and the rest is all the columns. Okay. So we call it letter classifier. Oh, there is some special character. Do you see some special characters? These are, I think. Yeah. Let me, actually, this screen is not greatly visible. All right. So error in match.org. Arg should be rf.poly. And so on. Did we miss something here? So so from the previous screen, we loaded this library, right? And what we are saying here is classifier equals this. So kernel name we will use as, what is my kernel name? Let's call it something of that sort. Polydot. Okay. Setting some values. So we can change it to anything. I just change it to polydot. Okay. This is kernel name as in on the basis of which we are going to detect this scanner. Okay. The way we are going to separate one point from another. And then we say, after it has finished, it's still doing something. And once that is done, we can do the predictions. We can do the predictions and see whether it's predicting correctly or not. All right. Yeah, it's done. Letter predictions is also done. Now let's see the table of letter prediction. So these are the letter predictions. So you can see that here what we have done is, so there is a letter prediction. Letter. So letter prediction is equal to predict, classifier, and letters underscore test. So let me just show letter predictions. So it's saying that on row number 3979, these are the possibilities, and so on. No, not really. All right. So here Z versus Z is high, and all right. Let me see how many agreements are there. So there are so many things which have successful. Let's see table. Table means table. What does table do? Table gives us summary. Basically, it does the word count. So you can see these many were our unsuccessful prediction.
Okay, so it is doing count.
Okay, and those many were our successful prediction. Okay, all we did was we did letters prediction equals to letters test dollar prediction letter. This gave a true and false, and then we did a count of true and false. So now you can see that these many were correctly predicted, these many were badly predicted. All right, makes sense to you? So we can basically, on the same lines, we can do a lot of predictions using neural net. Here we use something called KVM, SVM, support vector machines to do the predictions for us. Okay. So that's pretty much from the use of the in the machine learning, use of R in machine learning. So we covered the neural net, we covered the normal machine learning, clustering, we also covered hierarchical clustering, and we also covered complex examples like character recognition. All right. So do you have any questions for me? Okay. So go through these all examples and case studies, which we have taken one at a time, and you will be able to understand and refresh whatever we have done using this. All of this, along with this folder containing the data, will be shared with you. All right. It will be shared with you so that you can run these examples.
In my courses,
yeah, it will be available in my courses. So no questions for now.
General question. Use functions like denom, summary. How to see the functionality of those box?
Just type that name. Yeah. See, if it is written in R itself, it will show you that. If it is written in some other language, it will be there. But you always can do things like summary, and it will show you what does this do. All right.
I mean, for example, summary is doing the main, median.
How to see their values?
Yeah.
Okay, that will not be visible here.
So normally when we.
So if you do mean, okay, like here, so it wouldn't tell me. What?
I mean, normally when we are defining function, our own function,
Right.
so we are defining, right? So that definition I want to see.
The code.
Yeah.
No.
So we can't see it.
No, you can't see that. But here the definition it shows you, right? Mean
Yeah.
this. You mean the body, what's going inside?
Yes.
Oh,
What
that
it
is
is doing exactly.
no, it doesn't show.
Yeah.
If it is written here only,
Okay.
then it will show. Like for example, we wrote some functions, right? Like normalize. So it shows you that definition.
Okay.
Okay. If you without brackets you call normalize, it shows you the body.
Yeah, that's what I want.
But that's not possible entirely because these functions are written in C, most of the libraries. And therefore, it's not possible to do that.
So very few functions we can do that.
Correct.
Yes.
All right. So that's pretty much. So thank you very much. Stay connected and do write our review and on our Facebook page. And we will be launching more machine learning courses in details and specifically in Python and Panda parallelly. But this has been a great course. So stay connected, be active on our forums, and this will help you a lot. All right. Looking forward to get the feedback from you on the Facebook. All right. Thank you very much. The recording will be available online.